Hi class, welcome to an example problem for unit 9.2. Now in this unit we are learning about moments of inertia um, for composite shapes in particular. And moments of inertia are kind of an interesting concept. It's something that if you continue on with, especially mechanical engineering, you will use moments of inertia all the time. It's a really, really important concept that we're just going to barely touch on in this class. But it is a very important concept. You will see it over and over and over again if you're doing any sort of mechanics of materials um, or anything like that. So let's just kind of talk about it real quick. So a moment of inertia, it's essentially, and especially in this case, so we're talking about area moments of inertia. Area moments of inertia are essentially an object's tendency to resist bending. That's sort of a simple way of thinking about it. And it's really related to um, kind of the idea of area moments of inertia aren't exactly this, but it's very similar to the idea of, if you are um, swinging around, if you're spinning in a circle, if you're an ice skater, if you've ever seen a figure skater, and they hold out their arms and they spin slowly, they pull them in, then they start spinning faster. That is because they are reducing their moment of inertia. So it all has to do with twisting about an axis, right? So if you're a figure skater, you're twisting about, your center, and the farther away things are, and the bigger those things are away from your axis of rotation, the higher your moment of inertia will be. And then as those things either get smaller in size or get pulled closer to your axis, the moment of inertia will be reduced. So that's sort of an intuitive way to think about it. Um, but ultimately it's about an object's tendency to resist motion about, or to resist bending or rotating about an axis. So um, with composite shapes, this is very similar to what we did in Unit 9.1 with composite shapes about of centroids of composite shapes. We're going to do very similar type of things. And in this problem, I'm going to be working on problem 10.48 and 49 of the 13th edition of the book. So if you look at the book, the problem looks something like this guy right here. It's sort of this goofy looking shape with a big circle cut out of it. So I've redrawn that here on the board. So what we are given is this shape, and the way I'm going to think about it is it's a big rectangle with a circle cut out and a triangle cut out here. Now, similar to centroids of composite shapes, there's multiple ways you could approach this. You could break this into a rectangle here, and a rectangle here, and a triangle here with a circle cut out. For this approach, I'm going to imagine that I have one big rectangle with a cutout triangle and a cutout circle. And what we're asked to find is the moment of inertia, Ix. So that's the moment of inertia about an x-axis and about the y-axis. And it's important to note that it says it's about we're finding the moment of inertia about the x and y axes, the actual x and y axes. Obviously, if we can find the moment of inertia about any axis, we could find it about the centroid of the shape. We could find it about the axis way down here. And the answer will change, right? Because again, it's all about, it's very important, the distance from the axis of rotation, right? The farther something is, the farther some area or mass is from the axis of rotation, the larger it's going to be. So finding the moment of inertia about right here, about this x-axis, as opposed to, the center of the shape, it will be larger. The smallest a moment of inertia will ever be is about the shape's centroid. Any other point, it will get bigger. So how are we going to do this? Well, again, just like with the centroids, there's a table either in the back of the book or in the slides that tells you for kind of basic shapes what your centroids are. It looks kind of like this. So it has things like, hey, the centroid of a rectangle about its center is 1/12 base times height cubed. And for a triangle, it's 1/36 base times height cubed. So we're going to use this table. Again, it's in the slides if you don't have the book. highly recommend being familiar with that and having some of those relationships on your notes for the test. That'd be very good. So we're going to start by finding the moment of inertia about the x-axis. So first, what we're going to do is first, we're going to find the moment of inertia about the centroid of a shape. And again, I'm breaking this into these three basic shapes: rectangle, triangle, and circle. And then we have to do what's called the parallel axis shift to then find what that moment of inertia would be if it's about an axis other than its own centroid. So here's what we'll do. I'm going to say the moment of inertia about x is equal to, I'm going to start with the rectangle. So a rectangle's centroid, or moment of inertia, is its base times its height cubed. And it's important to note that the height, or the cubed term, is always the term that is perpendicular to your moment of, to your axis, right? So, because again, it's far more important how far away things are. If things are farther away, it increases the moment of inertia much more. So base times height cubed divided by 12. And this would be if we were finding the moment of inertia about the center of the rectangle, but we're not. We're finding it about the x-axis. So we do what's called the parallel axis shift, which is this area, so the area of the rectangle times the distance squared of and that distance is the distance from the centroid of the shape to the new axis. So this is for the rectangle. Okay. And then just like we did with the centroids of composite shapes, when we're cutting out terms, when there's like negative space, we subtract it. So we're going to say minus, now we're going to look at the triangle. So it's going to be bh cubed over 36 for a triangle minus, right? Because we need to do the parallel axis shift here. So minus the area of the triangle times its distance squared from the centroid of the triangle, which is going to be around here, to this x-axis. And then finally, so this is for the rectangle, or sorry, the triangle. And then finally for the circle, and the centroid of a circle about its center is pi r to the fourth divided by 4, and we need to take its parallel axis shift. So that's, again, area of the circle times its distance squared from the center of the circle to the x-axis. So let's actually plug in the numbers. So we get Ix equals, the base of the rectangle is 6, the height is 10, and we need to cube that. It's divided by 12, plus the area is just 6 times 10. And then we need to times it by the distance, which is going to be the centroid at the center of the rectangle, which is 5 up from the x-axis, so 5 squared. Now we need to take the triangle, so minus the base of the triangle is 3, the height is 6, and that's all divided by 36, minus the area of the triangle, which, as we know, right, is base times height divided by 2, and then its distance. Now let's think about this a little bit. So for a triangle, its center is 2/3 from the small end, or 1/3 from the large end. So it's right here. So it's going to be 4 plus 4, so it's at a distance of 8. Okay, and then let's do for the circle. So pi times its radius is 2, so 2 to the 4th divided by 4, minus its area, which we know is just pi r squared. So pi r squared, and its distance is from the center is 4. So we'll get 4 squared. And when we do all that math, we get that the moment of inertia is 1,192.4 inches to the fourth. Now it's kind of a goofy unit, but area moments of inertia will have units of a length to the fourth. So that is for Ix. Now let's go ahead and do Iy. It's going to be a very, very similar approach. The one trick is to recognize that the base and the height, the cube term is going to change. So we're going to cube the base instead of the height. So we'll get b cubed times h over 12 for the rectangle plus ad squared minus b cubed times h over 36 minus ad squared minus, that's for the triangle, minus pi r to the fourth, nothing's changed for the circle, minus ad squared. I mean, the distance has changed, but besides that, nothing really. Okay, so let's plug in the numbers for that. So we get Iy. So base is 6 for the rectangle, so we'll get 6 cubed times 10 divided by 12, plus the area is 6 times 10. And the distance from the center of the rectangle to the y-axis is 3, so we'll get 3 squared. Then minus, let's see, so the base of the triangle is 3, so 3 cubed times 6 divided by 36, minus, all right, same area, 3 times 6 divided by 2, and now the distance is from here to here, so it's 3, and again, 2/3 from the small end, or 1/3 from the big end, so that puts an extra 2 inches here, so it's 5 inches from the y-axis. And then finally the circle, same area, so pi r to the fourth divided by 4 minus the area, pi r squared times the distance, which is now from the center of the circle to the y-axis is 3. And we get that Iy equals 364.83 inches to the fourth. So that's how you go about that. Hopefully it kind of makes sense that intuitively that the y-axis should be smaller, right? Just because the overall base is shorter than the overall height, right? You can kind of imagine if I was grabbing here at the x-axis and trying to spin, right? If there's just a handle right here and I just try to spin this whole shape all the way about the x-axis, it's going to be a little bit harder. There's more resistance than if I were to grab here at the y-axis and to try spinning it like that. So hopefully that makes some sense. And of course, if you have any questions, as always, just reach out to me. I'm happy to help and talk more about this. So thanks for watching.